The next thing we're going to do is we're going to look at the Wilcoxon signed rank test. So let's say, for example, you wanted to run the paired sample t-test, but you failed the normality assumption. Or maybe you don't have the correct data type to run the paired sample t-test. In that case, you could probably run the Wilcoxon signed rank test instead. So the Wilcoxon signed rank test, we use this to determine whether the median of two continuous variables from the same group of participants differ. So this is similar to the paired samples t-test in that if I was a participant in a study, I would need two different scores that are testing the same thing. So that might be at time point 1 and at time point 2. We're looking at the median of, in this case, time 1 and time 2 for me as a participant because I have both scores. I have a score 1 and a score 2. This is a non-parametric test. That means our data do not have to pass the normality assumption. It does not have to look like the standard bell-shaped curve. And to get some additional help running the Wilcoxon signed rank test, I've left you a few resources here in our guide. All right. With every test we do, there are certain assumptions that must be met in order for the result of the test to be valid. The first assumption for the Wilcoxon test is that the dependent variable must be ordinal or continuous. For continuous in RStudio, that means it must be integer type or double type, which means decimal, or numeric type. And for ordinal data, it means it has to be the ordered factor data type. So you can use either of those data types. There's a common package for reviewing data. If you were just here for paired sample t-test, you've already installed this and run it. So if you're new, you're going to have to run maybe line 112, but definitely line 113. I can run it again. And we're going to take a glimpse at our data to make sure we've got the right data types. So we've got glimpse of fake data with 30 rows and 8 columns. If you're just here for paired sample t-test, we made a new column. So there's one column more than normal. And then we've got the $ to indicate which column from that data set. If we look at $ fake data 1, this is listed as DBL or double, which means decimal. And if we look at the next column, we've got $ fake data 2. This is also listed as DBL double decimal, which means these are both continuous data. So we've passed this assumption because we're going to be using continuous dependent variables. For assumption number 2, the independent variable must be categorical with two related or matched groups. That means, for example, each observation or each participant needs to have a score 1 and a score 2. So if I was a participant in the study, I would need a score for fake data 1 and a score for fake data 2. We can look at our data using what's on line 120. This is view left bracket fake underscore data. And be careful, the V here is actually a capital V. It's one of the few functions with a capital. If we run this, it opens the data set like an Excel spreadsheet, and we can see a gender column, a fake data 1 column, a fake data 2 column. If we assume each row here is a unique participant, if I was participant 1, I would probably be in row 1. I have a score for fake data 1, and I have a score for fake data 2. So we've passed the assumption. We have 2 observations, i.e. fake data 1 and fake data 2 for each person. We have 2 unique but matched or paired groups, which means we pass this assumption. Assumption 3 is a little unique. It's a little bit different than some of the other assumptions we've seen before. The distribution of the difference score between fake data 1 and fake data 2 in this example must be symmetrical. So if you were just here for paired sample t-test, we've already made our difference score column. But if you're new, what we have to do is take our 2 different variables or our 2 columns of data that are looking at the same thing. My fake example, it's a happiness score. We've got happiness at time 1 and happiness at time 2. And we need to do a different score. We need to do a subtraction. So if you were just here for paired sample t, we already did this, but this is on line 128. We're going to create a variable or a column called diff, diff for difference score. And we're going to calculate that as fake data 2 subtract fake data 1. So we can highlight line 128 and we can run it. If you were to open fake data again, it's the same difference score we just made. So it's taken the fake data 2 score and subtracted the fake data 1 score and stored that in the column that's called diff. And for this assumption, what we do is we need to plot it. We need to look at a histogram of our data to be able to say, does it look approximately symmetrical? So we can just do a basic histogram. It doesn't have to be fancy. So we can use the hist function, HIST, left bracket, capital F fake underscore capital D data $diff end bracket. And if we run this, This will open a histogram for us in the bottom right in the plots window. It's a little small, it's a little squished, so I can click zoom. What we're looking for here is you want to look on your axis at the bottom. This is your x-axis. And you want to kind of cut the graph in half visually. If you wanted, you could put a ruler against the screen. You could draw a red line on it. If you were using something like Excel, you could just look at your scale and be like, okay, so if this is 0 over here and this is 10, the midway point would be about here. This is our 5. If we were to cut this graph in half right in the middle, which is at the 5, does the left half of the graph look approximately the same as the right half of the graph? That's what we're doing with this assumption. Does the left half look like the right half? It's close. We've got what kind of looks like a normal distribution on the left half. So highest amount of data in the middle, lowest amount of data at the ends. The right half, it's kind of high on the left and then really low on the right. So what we're asking ourselves right now is, does this look roughly symmetrical? It doesn't have to be perfect. They don't have to overlay exactly on top. In this case, it's kind of close, but I would be a little worried that maybe we can't use this test because the left half is pretty low and it has like an inverse U shape. And the right half is pretty high on the left and low on the right. So I would maybe say that we can't use the test today. We're going to run the test anyway, just for practice, but you definitely want to make sure you check all of your assumptions because you wouldn't know if you failed this unless you actually checked the assumption. So again, we're a little worried today. It maybe doesn't look perfectly symmetrical. It doesn't have to be exact, but it doesn't look that great. But we're going to run the test anyway today for practice. So always check your assumptions. And I've left you an expert tip here just in text. Non-parametric tests do not care about outliers. So if you found and removed some outliers when you were doing the paired sample t-test, you could put those outliers back in because this test does not care about outliers. The non-parametric tests don't use means, so they don't care about outliers. So you should still always remove some impossible values if you have those, but if you found and removed outliers, you can actually put them back in if you would like. Okie dokie, we're ready to run the test. How do you actually run this? Again, we're looking to see whether the median of fake data 1 is different than the median of fake data 2. If you were just here for paired sample t-test, you might already have some of this installed, but you need to install the package RStatics, take it from the internet, put it on your computer, and then you need to load the library RStatics. So you need to say, this is already on my computer, I would like to use it right now. So I can run line 143, library left bracket RStatics right bracket. I can run this. You'll notice I get a bunch of red text in the bottom left in the console. It says attaching package RStatics. The following objects are masked from package effect size, Cohen's d eta squared. The following object is masked from package stats, filter. This is not a true error code. It still did the thing I asked it to do, but I have a lot of different packages installed and some of them have the same functions within those packages. So this is just a warning saying, hey, you have 2 or more packages that are fighting and we're masking some stuff, i.e. hiding some stuff. We're going to use the other one instead. So that's okay. I'm not worried about this. If you get an error code either right now or in a minute asking you to install the coin package, make sure you run what's on line 145. It's install that packages left bracket quotation mark coin end quotation mark end bracket. That will just say, hey, you said I needed coin to run anything right now. I will put coin on my computer so that I can run what I'm trying to do. I don't have that error code right now. I don't need to run it, but you might get it if you haven't done this before. Okay. So we would like to use the Wilcox.test function. If we haven't used this before, we can ask for a little bit of help. We could either do an internet search for this specific function and find the R documentation, or if we don't want to open anything else, we can run this directly within our source window here. We can say question mark Wilcox.test left bracket right bracket, and it will open in the help window in the bottom right some additional help for you. This is directly the RStudio documentation. So it says Wilcox.test squiggly bracket stats. This function, Wilcox.test, is in the stats package, which is actually in tidyverse, and we already have tidyverse, so that's okay. What does this do? It says Wilcoxon rank sum and signed rank tests. You can do 2 tests here. Description: performs 1 and 2 sample Wilcoxon tests on vectors of data. The latter is also known as a Mann-Whitney test. Usage: Wilcox.test left bracket x comma dot 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 right bracket. and it's got a lot of different information in here, and some of it might not be super user-friendly. It gives you all of the arguments with some additional language that might not be super user-friendly. So let's walk through it together and see what we're actually doing here. I'll make this smaller. So we're going to give the two different groups we're comparing and say paired equals true. That's all you need to do today. You say wilcox.test, left bracket, fake underscore data, $, fake underscore data 2, comma, fake underscore data, $, fake underscore data 1, comma, paired equals true in all caps, end bracket. And if we run this, we get some text in the console in the bottom left. We get a blue line of code for what we just ran. And it says, Wilcoxon signed rank exact test. Data. We're comparing fake data 2 and fake data 1. We get a V statistic of 465. We get a p-value with scientific notation. It says 1.863e negative 0.9. If we were to write that out, it would be decimal 0.00000001863. This means we found a statistically significant difference between the medians of fake data 1 and fake data 2. And we know that because our p-value is less than 0.05. If our p-value is greater than 0.05, we'd be able to say we failed to find a difference between the medians. But here we found a difference. We can say there's a difference. One of these is higher and one of these is lower. We don't know which way yet. We'll do that in a minute. But we know that there is a difference. So we have most of the information we might want if we were reporting this test. But the last thing we'll probably also want is what's called the effect size. For a Wilcoxon test, the effect size is R, lowercase r. It's not the same as Pearson's R, but we're going to calculate lowercase r. This requires the data to be what's called long format. Right now we have wide format with stuff going across the page. We need to put things going down the page, which is a little confusing. I'm not going to go into too much detail about line 153, but you're welcome to highlight it and click run. We're also going to run line 155. And all you need to know is that behind the scenes, what we've just done is taken the data going across the page and made it go down the page. And I can show you what that looks like if you run line 157. So we're going to do capital V view, left bracket, fake data underscore long. We've created a new data set called fake underscore data underscore long. And if we run this, we get just two columns. I only kept the two things we need. We have fake underscore data underscore group. And you can see we've listed whether the data here is for fake data 1, or if we scroll, some of it's for fake data 2. And if we scroll, that's it. We're looking at just the two groups. I've kept nothing else. And we've got fake underscore data underscore score. And you've got a score for each of these things. So we've got some data here. What we're going to do now is run our test on this long form data that's going down the page. So it's the same data we had going across the page. We've just reformatted it because this specific test needs it in a different format. So we're going to calculate our effect size using our two new groups in our new data set. So that's line 159. Wilcox underscore EFF-SIZE, left bracket, capital F fake underscore capital D data underscore lowercase score, tilde, capital F fake underscore capital D data underscore group, comma, data equals capital F fake underscore capital D data underscore capital L long, comma, paired equals true in all caps, end bracket. This is the format that we need for the Wilcox effect size. If we click run, we get some blue text in our console, and it gives us, it's called a tibble. It's a certain data type within RStudio. So it's displaying some data for us. It's saying we are looking at fake data score, and we're comparing fake data 1 to fake data 2. It's given us the size. We have an N of 30 for fake data 1 and an N of 30 for fake data 2. And it gives us the word for our effect size to say, how big is this? So our effect size is listed as 0.873. And the word tells us that that is a large effect size. Generally, anything above a 0.6 is considered large. How would we actually write this if we were to put this in a paper? That's on line 161. You would give it the statistic. So if we scroll up here to the Wilcoxon signed rank exact test data, we'll get most of the information from here. V is equal to 465. P is equal to all of those zeros, 1863. So we've got a p-value of less than 0.05. R, our effect size down here, is 0.873. We know there's a statistically significant difference between the medians of fake data 1 and the median of fake data 2. We don't know which direction that goes, so we can actually ask RStudio to give us the medians. So in line 163, we say median, left bracket, fake underscore data $ fake underscore data 1. And on line 164, we have median, bracket, fake underscore data $ fake underscore data 2. So we're going to ask for the median of those two groups. Fake data 1's median is 87.1945, and fake data 2's median is 92.14947. The p-value tells us there is a difference between the two groups. The effect size says that this is a large difference between the two groups, and the medians tell us that fake data 2 is higher than the median of fake data 1. The last thing we might want to do is we might want to graph it. The best graph, if you're doing work with medians, is a box plot. We're not going to get too into detail here. We're not going to get too fancy. We're just going to do a simple basic box plot. If we highlight line 169, we're going to do a box plot. We're going to graph fake data 1, fake data 2. We're going to give them some names. And we're going to say it's the median. If we run this, we get some information down in our plots window. It's a little squished. I can click the zoom button to make it a bit bigger. And what we see here is we've got our group down here on the x-axis. We have fake data 1 and fake data 2. It gives us the median on our y-axis, and it essentially gives us two box plots, one for each group. The thick black line in the middle is the median. So we know that fake data 1 is lower than fake data 2, or we could flip it and say it the other way. Fake data 2 is higher than fake data 1. We can visually see that. We've got our interquartile range for each of our boxes, and we've got some whiskers showing the distribution of the data. So here we've got a box plot of fake data 1 versus fake data 2, and that's showing us very easily the same thing as the Wilcoxon test, that there's a difference in the medians. Fake data 2 is higher than fake data 1. And that's how you run a Wilcoxon test.